Hi, good morning. Today my focus of the video is a seismic torsion and what are the recommendations given in IS 1893 regarding the building irregularities and why the building twist. So basically, first of all, we'll see during earthquake what type of movements occurred in the building and what is meant by a seismic torsion and what is its effect. During earthquake, in the building, there are two possible movements. One movement which is called as a translation movement. Okay, as shown here, this is called as a translation movement. And second movement is that a twisting movement. And this twisting movement will cause the torsion, that is twisting effect, especially in the important structural element columns. So column will get twist during earthquake. And because of this twisting in the column, there will be a shear stress and the column may fail under shear. And the shear failure is always a undesirable type of the failure because it is a brittle failure. So why the building twist? That is a basic question. So we will see this particular effect of twisting by this swing analogy. So this is a swing, and when we see that is a person is sit at the center of the swing, and when the movement is there to the swing, this movement is the uniform movement, what is called as a translation movement. Okay, so same behavior we can observe in the earthquake in the case of building subjected to earthquake. A single story building or multi-story building, when the building is symmetric and the mass of the building is distributed uniformly, then there will not be a torsion. Any of the element will not twist, and there will be a pure translational movement. And translation movement in the building or in the structural element, this is expected. This will not cause any much damage to the structure. But in other way, if the same boy is seated on one side of this platform, and when there is a swing, then both movement will be there. That is, the swing will move forward also, and along with this, there will be a twist. So why this twisting is there? Because this mass is not at the center, but mass is on one side of this platform. So this is called as a mass unsymmetrical. Mass is not properly distributed, uniformly distributed. Therefore, there is a twisting along with translation. So same thing in the building. This is a multi-story building. On one side of the building, there is a heavy mass. There is a heavy mass, and the other part of the building is a light mass. And therefore, whenever the earthquake comes in this particular direction, then because of this particular building will experience translational movement as well as the rotational movement. And this rotational movement is nothing but a torsion. So same case we can observe here also. Second analogy, the swing, suppose this particular swing, on one side, this is the thread of the swing. This is thread of the swing, which is short, and other side, the thread or the rope to which is connected to this platform. This is a longer side. And even though the boy is seated or the mass is at the center, this will also experience both the movements. There is a torsion and there is a translation. Both movements will be there. So again, there is a unsymmetry with respect to the length of this string. And therefore, so that is, in short, whenever there is a unsymmetry with respect to a mass distribution, unsymmetry with respect to stiffness distribution, the structure, building structure is subjected to torsion. Okay, so the same analogy we can apply to the building. So building resting on sloping ground, building resting on sloping ground. On one side, the length of the column is short, and other side, the length of the column is a long column. Okay, length is more. And whenever the earthquake is there, so in this case, there is a both moments. There is a translation moment as well as there is a rotational moment, that is torsional moments are there. And therefore, the longer columns, the deformations or displacement or rotations in the longer columns are more. To this building also, another example we will take. To this building, again, the mass distribution is not uniform. Because of this open story, the mass is comparatively lesser on this particular part, while as more mass is on this side. So this is again the example of the mass not equally distributed, unequal distribution of the mass and subjected to earthquake. Again, there are two combined type of the movements, translation movement and the rotational movement, the twisting. Another example. Now these are the building plan is there. So this is a shear wall. This is a shear wall. This is also shear wall. So on a right angle, that is on two sides of the building, the shear wall is there. And whenever we provide a shear wall is provided just to increase the stiffness. So when we provide the shear wall on one side, okay, one side, only the stiffness of that particular side will be increased. And therefore, this is called as the stiffness irregular structure. Stiffness is not properly distributed. Stiffness is not uniformly distributed. And therefore, again, when the earthquake comes, this building, because of the unsymmetric distribution of the stiffness, will subjected to the movement, combined movement of a translation plus twisting. In this case, these particular columns, there will be a large movements will be there and subjected to twisting. Same case here. That is, the shear wall is, this is the plan of the building. Shear wall is provided only on one side. So this particular side becomes very stiff comparative to other sides. And whenever the earthquake comes, the whole building will rotate about this particular point. And therefore, these columns will subjected to large rotational movement. Same case here. Okay, so this is a part which is a stiffness is very high, and therefore the rest of the part is a flexible. So there will be a large, as shown in the figure. This is the deformation in the building. So these particular columns, there will be a large rotational deformations. So in short, there are two reasons why the building twists. First reason is that unequal distribution of the mass, that is, mass is not distributed uniformly. And second is that unequal, unsymmetrical distribution of the stiffness. These are the only two reasons which causes twisting in the building. Also, some another examples. This is the T-shaped building, L-shaped building. Okay, so here also the area is unsymmetrical. So area is, this is plan of the building. Area of the building is unsymmetrical. That means mass distribution as well as stiffness distribution is not symmetrical along X and Y direction. Okay, so therefore this building will also twist. This is a elevation of the building. This is elevation of the building. This story is a 3-story. This is 2-story, and this is a single story. Okay, so there is a unequal distribution of the stories, and therefore there is an unequal distribution of the mass as well as unequal distribution of the stiffness. Such type of buildings will also subjected to translation moment, which is less, but torsional moment will be more, torsion will be more. There are some buildings like this. This is the plan of the building. Plan of the building, even though the plan is a rectangular plan, but this side of the building, there is a heavy mass. And therefore, this is unequal distribution of the mass. Unequal distribution of the mass. Therefore, this building will also twist because of the unequal distribution of the mass. This is a building resting on a sloping ground, as we have discussed. This is another example. This is a story. This is a story on which there is a heavy mass. Sometimes we know that in the case of commercial buildings, some floors are given on rental basis for the workshop purpose, or sometimes there will be a library floor. So these are the shops where the mass is very heavy comparatively comparative to other floors. So this is called as a mass unsymmetrical with respect to height of the building. Again, this type of building will also twist. Again, some few examples. Normally in cities, that is apartment buildings, ground story is kept open for parking purpose, while as the story above, there is a masonry is also there, brick masonry is also there. So whenever the building is subjected to lateral forces due to earthquake, the stiffness of this particular part is high because there is a combination of the frame plus brick masonry. Togetherly will resist the lateral forces. So stiffness is higher, but here only the columns are there in the parking floor. So stiffness is less. So there is a drastic change in the stiffness. Okay, tremendous change in the stiffness in the ground floor, parking floor, and story above. So this is also called as a stiffness irregular building. And whenever irregularity is there, the building twists. And one more effect, what is called as the soft story mechanism, will also occur to this particular type of the construction. This is about the shear wall. We come to this thing in detail in the next slide about the shear wall. And this is also the shear wall is there, but shear wall is provided not from the bottom story. Shear wall is provided in the first story and the second story only. So therefore, stiffness of only these two stories will be increased comparative to this. This is comparatively flexible story. So this is also comes. This is also the type of the frame which is stiffness irregular. So this type of building also will twist. Now about the shear wall. So as per as the seismic resistance is concerned, shear wall plays very important role to resist the lateral forces. So shear wall are very stiff in its own plane, and because of the shear wall, not only stiffness increases, but it also reduces the displacement in the structure. But the shear wall and its advantage, we get more advantage if the shear walls are located in the proper position. So location of shear wall is very important. If it is not placed in a proper position at proper location, then again the building will twist. In IS 13920, some recommendations are given how to place the shear wall. It is said that in one direction, at least there should be two number of shear walls. So for example, if this is X direction, so this should be the minimum two number of shear walls should be there, and the shear walls should be placed at the periphery. That is the second recommendation. In Y direction also, these are the two shear walls are there. So it is clear that we have to place the shear wall at the periphery only, because whenever there is a twisting, large deformation is there at the periphery. Large deformation, that is torsional movement, will be there at the periphery, and we have to control that particular movement and to increase the torsional rigidity, that is to reduce the torsional movement effect. The shear wall should be placed at the periphery, and to avoid the torsion, it must be placed in the symmetric manner, in the symmetric way. And shear wall is just like a wide column, and therefore it should be provided right from the bottom story up to the top story, and it has a foundation just like a column resting on hard strata. Never to be provide the shear wall in this way. Okay, like this. This is unsymmetrical location of the shear wall. Shear wall is not symmetrically placed. Number one, this shear wall is not provided at somewhere at the periphery somewhere, and in one direction at least two shear walls are there. So this is also not followed. If we provide the shear walls in this way, so because of the shear wall, this particular corner will becomes more stiff comparatively to the other part of the building, and therefore the complete building will twist with respect to this particular area where we have provided the shear wall. And the proper location of the shear wall should be like this. So this shear wall in front of this symmetrical place, and in y direction this is the shear wall and this is the shear wall. So this is symmetrically placed shear wall, and therefore this is the proper location of the shear wall. And if we provide this, we get the expected benefit of shear wall. So these are the two reasons why the building twist. One is if the building is mass irregular or mass is not uniformly distributed, and number two, stiffness is not distributed uniformly. In IS 1893, clause number 7.1, there are certain recommendations given, or there are certain checks given to check the torsion irregularity, and if any structure satisfy this, then it is said to be torsionally irregular. Then proper steps or proper measures should be taken to avoid the torsion in the building. Okay, so these particular checks I will explain in ETAP. Now this is a building, and it is a 9-story building, and it is already analyzed for the earthquake forces. Now we'll see the displacement. So what is the first clause? I will explain separately. The first clause is that if this is a building and it is subjected to the force from this direction, then there will be deformation. So this corner will experience this much deformation, and for example this corner experience this much deformations. Okay, so this is called as a delta 1 deformation, and here this is called as a delta 2 deformation, right? Then what the recommendation number 1? This recommendation number 1 says that the maximum horizontal displacement of any floor in the direction of lateral force at one end of the floor is more than 1.5 times its minimum horizontal displacement at the far end of the, then building is said to be torsionally irregular. Okay, so that is delta 1, if it is greater than 1.5 times delta 2. Delta 1, if greater than 1.5 delta 2, then it is said to be a torsionally irregular. Now to this building, we will check this. Okay, now we'll apply the, already this building is analyzed. Now we'll apply the earthquake force, that is response spectrum force. So this is response spectrum in X direction. This is response spectrum in X direction. Okay. Now this is displacement to response spectrum, and this displacements are in millimeter. Okay, so what is the deformation here at this corner ux? What is deformation? 4.2. So maximum deformation is 4.2. That is not maximum deformation at this corner. It is 4.2. Say it is delta 2. And what is the deformation at the other this thing? This force is applied in the x direction, that is in this direction. So we have to check the deformation here, and other corner is this deformation. So what is the deformation here? It is something 4.2 millimeter. And what is the deformation here? 7.5. Okay, 7.5. So 4.2 multiplied by 1.5. So actually limit should be 6.3. 6.3, but how much it is coming? 7.5. That is in the x direction, it is not satisfying the criteria. The deformation is exceeding the limit. So therefore, in x direction, the building is torsionally irregular. Okay, same thing we will check in the y direction now. So this is the y direction. The force is in this direction. Right? Now we'll check the deformation at two corners. Okay, we'll check the deformation here, and we'll check the deformation at this corner. Okay, now change the force to response spectrum in y direction. Deform shape. So this is deformation in y direction. Okay, now we'll check it at two locations. This location and this location. Now what is deformation here? Uy, it is 4.8. In y direction, it is 4.8. And here it is how much? 0.6. In uy direction, it is 4.9. So almost same. It is 4.9 and this is 4.8. That is the deformation at this point in y direction, that is uy 4.8, and this is 4.9. So that means in the y direction, the minimum, that is maximum deformation, is less than 1.5 times the minimum deformation. So therefore, the building is torsionally regular. It is not irregular. In y direction, it is satisfying the criteria. Okay, displacement is within limit, but in x direction, it is not satisfying. So therefore, what the clause says that if it is not satisfying in any direction, then anyhow you have to change the configuration. That means configuration in the sense you can add the shear wall, or you can turn the columns. You can change the orientation of the column and just reduce or increase the deformation in that side. First option is you can turn the columns orientation and check again the deformation in displacement in x and y direction, or you can add shear walls at some locations at the periphery, but configuration should be changed in X direction. So this is about the clause number 1. Then second clause is about the natural period corresponding to fundamental torsion mode of the oscillation is more than those of the first two translation modes of the oscillation along each planned direction. I will explain here. Okay, now we will see the modal analysis results. Okay, now these are the results in the table format. Okay, now these are the results. No, this is not the expected table. We require the results of the modal analysis. So this is a yes. So this is the first mode. What is time period? It is 1.16. Then second time period is 1.10. Third time period is 1.066. First thing is that the difference between the time period should be more than 10%. That is, the modes should be well separated. It is called as a well separated. There are two types of the modes as per IS1893 definition. Modes closely spaced and most modes are widely spread. As per as the torsion is concerned, the mode time period between the first mode, second mode, third mode, the variation should be more than 10%. That is the first. And what that clause is saying, second clause, is about the time period in the principal torsion mode. Okay, now what is meant by principal torsion mode? See, this is the first mode, whether it is translation mode or a torsion mode. How to see this? See, what is the mass participation? 84%. Okay, so it is 84%. This is in the UX direction. Okay, so right. So it is a translation mode. First mode is a translation mode. Second mode, what is time period? What is the mass participation? 73%. Again, this is greater than, this is a dominant mass participation is in the UX. Again, this mode is a translation mode. First mode is translation in UY direction. Second mode is also translation mode in X direction. But you see the third mode. Okay, so third mode, the mass participation is only 12% in X direction and almost nil in the Y direction. But you just observe the rotation in Z direction. So for the third mode, the rotation with respect to Z direction is 78% mass is rotating with respect to Z. So this is for the third mode. So therefore, third mode of the structure is a principal torsion mode. And this time period, what the clause said, this time period, that is 1.066, should be less than the principal translation mode. Okay, now it is less. How much it is? 1.066. Okay, and this time period, that is translation time periods, are greater than this. So therefore, as per that particular clause, the time period of the principal torsion mode is less than the translation time period. So the building is a regular building. It is not irregular building. Okay, as per as the second clause is concerned. This is about the clause number second. And next, one more clause is that this is with respect to the okay, now this is, we have checked this. So that clause is with respect to a with respect to the mass participation. So for the first mode, the mass participation is 84%, and therefore it is greater than 65%. So therefore, this is desirable. Second mode is in the y direction. Sorry, first mode is in the y direction, mass participation 84%. Second mode is 73% mass participation, and this is in the x direction, which is again greater than 65%. And therefore, this particular building is said to be a regular building. It is not torsionally irregular building. So as per as the irregularity checks are there, given in IS1893. So actually 3 conditions were given. So as per as that condition, only one condition is not satisfying. Okay, so then the second condition, that is about the natural time period, this condition is satisfied. So therefore, building is a regular building. It is not torsionally irregular building. And second, about the displacement at the corner, it is satisfied in the y direction, but this is not satisfied in the x direction. So in the x direction only, the building is a torsionally irregular building. And therefore, slightly as per as this building is concerned, it is required to modify the configuration along the x direction. Okay, so this is the conclusion from this particular plan of the building. So in short, at the end, just I conclude, before to go for a detailed analysis of a building, seismic analysis of a building, before to go for a detailed seismic analysis of the building, first of all, perform modal analysis and torsional irregularity checks given in IS1893. It should be checked thoroughly, and if it is satisfied all conditions given in 1893, then the building is said to be regular building, and then go for the next step, that is after analysis there will be design for optimization of the member sizes. Okay, and if any condition is not satisfied about the torsional irregularity, then we have to take a appropriate step at that stage only. If required, modify the this thing configuration and make it safe at that stage itself, and then go for this thing, because a torsion is very important phenomena during earthquake, and the torsion is one of the source of brittle failure in the structure during the earthquake. Okay, thank you.